Welcome back, guys. Now this video will be a bit different from the previous ones in that I'll actually be going over an entire paper, right, rather than just looking at the pseudocode questions. So as we see, well, this is paper 1 from February-March 2024, the paper 12, right, and this is the IGCSE or an O-level paper. Now, I mean, this is actually the most recent paper that's been released by Cambridge, so the mark scheme is available. Now, you know, if you can just use the mark scheme, of course, that's fine. However, if you do want, you know, more detail, more explanations, then yeah, hopefully this video will be useful. Right, although, I mean, this video might go on too long, so in that case, maybe watch at 1.5 speed, right, and yeah, hopefully you can still follow at that speed. Right, question 1 says, computers represent different types of data in binary. Tick one box to show the reason why computers use binary to represent data. So for these questions, often, you know, two of the answers can be quite similar. Or yeah, the wording can be quite tricky. So what I actually like to do is I like to sort of, you know, mark the ones that could possibly be true, and you know, the ones that are sort of definitely not true. So let's say this first one, where computers only allow ones and zeros to be entered. Like, this is kind of true. I mean, let's say if the user types A, well, right, big A is going to be the ASCII code 65. Now, yeah, of course, while they have typed the character A, you know, technically that A is actually stored as, you know, 65 in binary. So for this one, I'm going to put kind of like a question mark, because yeah, maybe it's true, you know, or maybe there's a better answer. Right, the next one, computers are made of switches and gates that can only be on or off. Now, I would say this one is definitely going to be true. And you know, it does say only one, right, but let's just check the others just in case. Right, binary does not need to be converted into other forms of data to be displayed. Now, again, I mean, let's say you've got like a, I don't know, yeah, just text. Well, if you want to output the character A, of course that A has to be converted from the actual like binary, you know, ones and zeros, right, into the ASCII representation. Although again, you know, ASCII, right, that is just the binary itself. So yeah, I'm going to put sort of a question mark. Right, both computers and humans can quickly process binary data. Well, this is definitely false, because I mean, yeah, humans are quick with binary. Computers are quick with binary, right, but humans, well, definitely not. So I think here, I mean, the most logical answer seems to be this one, right, B. Right, then, one form of data is characters, the American Standard Code for Information Interchange, or ASCII. Denary number for the character, big N is 78. Right, again, tick one box to identify the ASCII denary number for the character big Q. So with ASCII, I mean, hopefully you know that it's just kind of like sequential. So like big A is going to be 65, right, then big B is going to be 66, right, big C 67, right, so just increments, right, plus ones. So here then we just want to write down the alphabet. So if we think M, right, then it goes N, right, then O, then yeah, P, right, Q, yeah, you know, like RS. Right, so we say N is going to be 78, right, therefore O is 79, 80, and then yeah, this should be 81. So I think that should be fine. Right, then we want the binary number for the ASCII denary number for big N. So this here, I mean, well, I said big N is 78, right? So we just need to convert 78 into binary. And if you want, yeah, you can go here and actually write down the, you know, positional values. Right, so 1 to 8 is 64, 32, right, 16, right, 8, 4, 2, and 1. So with 78, well, there's no 128s, but there will be a 64, right, because, well, 78, yeah, we can do 78 minus 64, right, that's going to give us 14 remaining. I mean, we can write this 14 remaining here if we want. Right, then there's going to be 0 42s, right, but then, well, we want to make 14, right, so also 0 16s, but then when we get to 8, okay, there will be an 8, right, this will give us 6 remaining. Right, there will be a 4, okay, that's going to give us 2 remaining. Yeah, there will be a 2, right, then there won't be a 1. I mean, this is like quite a kind of convoluted way of doing it. You know, maybe you can just do this directly in your head, probably. And the thing with these binary questions, you know, they're quite easy to check because we can just add it up. So, right, let's go 64, right, then we go plus 8, okay, that's 72, plus 4, 76, right, plus 2, yeah, 78. And of course, you know, here, let's, hang on. Yeah, I'm going to move it up because the top of the graphics tablet doesn't really work that well. Right, so 0 1 0 0, right, 1 1 1 0. So once you've done the working, I mean, do remember to actually write it back where they tell you to have the answer, because well, sometimes I see people, they actually forget to write the answer, and they just write the working. Right, the next one. So explain how the word red is represented using a character set. Now I'm going to write it here because this thing pops up, it kind of gets in the way. So probably what I'm going to say, let's say each character. Right, I probably want to say like each character is represented using a unique ASCII or Unicode, kind of binary code. And probably I'll mention that they're going to be 8 bits. Okay, I mean, if we got standard ASCII, that can be 7 bits, but extended ASCII and Unicode, right? For example, like say UTF-8, right? That's going to be 8 bits. Right. Okay. So let's say each character. And then, well, let's list them, right? So R, right, then let's go E, right, and then D, will be represented, right, as a unique, I mean, let's just say 8-bit, although, again, standard ASCII, it could be 7 bits. Let's say extended ASCII, right, or let's say Unicode. I mean, we could mention UTF-8, right? But there's also UTF-16, UTF-32. Right. Okay. So we'll be represented as a unique 8-bit extended ASCII or Unicode. I mean, let's say like binary. Just binary code. That should be fine. Right. Hence the entire string. Right. The entire string red, and let's say this will use 24 bits. Because obviously, 3 characters using 8 bits, right? It's going to be 24 bits total. I use 24 bits, right, to store. Yeah, and I think that should be okay. Yeah, I think that's fine. And again, of course, once you've done that, well, then check how many marks it's worth. So here, probably you get 1 mark. Maybe for saying like each character has a unique, unique binary code. Yeah, I mean, I think that's probably 2 marks there. All right, hopefully. Right, the next one, sound can be represented as binary. Explain why recording sound with a higher sampling resolution creates a more accurate recording. So what I'm going to do, I'm just going to kind of draw a quick diagram of how sound is represented. Okay. I suppose maybe not represented, but how it's kind of quantized, right? How it's digitized and stored in a computer. So let's say we've got the original maybe a sine wave. I mean that's just some sine wave, right, representing the analog signal. Now let's say we've just got some different levels, right? So maybe this here is and I mean, like, we could store this as negative, so we could say like this one here is 0, but I'm actually just going to use unsigned. And I mean, honestly, I'm not sure how how sound formats do it specifically, but I think some diagrams I have seen like this. All right, so let's say like 0, 1, 2. Maybe this can be a 3. And in fact, let's try and space them a bit more evenly. Alright, and I mean, actually, to be honest, I think I will do negative, right? It just makes it a bit easier to see. Right, let's say like -1, maybe -2. Right, and let's go sort of 1 is about here, maybe 2 is here. Right, okay, and then of course, maybe like a 3. So, I mean, this here, right, you can think kind of the y-axis. This is going to represent the sampling resolution. So the number of like distinct values that we can represent, okay, or the number of distinct, the number of distinct amplitudes we can represent. I mean, that's going to be, basically that's based on the sampling resolution, right? Because let's say we have a sampling resolution of, let's say 2. Well, right, that gives us 2 to the power of 2. So in that case, we only have 4 different values that we can represent, okay, 4 different amplitudes. Now, I mean, in this case here, we've got 6. So, I mean, we would probably go, for example, like a -3, and then I guess we can have a 4. All right, okay, so this here will give us 8. And so in that case, well, that's going to be 2 to the power of 3 equals 8, right? So let's say if this was our kind of, you know, I mean, if you want to use the sort of A-level term, right, it's going to be quantization levels. So each of these, right, 0 is one quantization level, okay, right, 1 is another quantization level, 2 is another, right, 3 is another. So if we've got 8 quantization levels, then that means that the sampling resolution is going to be 3, okay, because we're using 3 bits per sample. Yeah, that's the definition of sampling resolution. It's the number of bits used to store one sample. So yeah, okay, all right, if we've got 3, that gives us 8 different values. Now, let's say, for example, we've got 2 to the power of, I mean, let's just say 8, right? Well, that gives us 256 different values. So effectively, right, these quantization levels could be much closer together. I mean, I'll just do it here because I don't want to mess up my other diagram. But in that case, like, rather than just having, you know, 0, 1, 2, 3, right, we can have sort of 0, right, then we have 1, then we have 2, then we have 3, you know, 4, 5, 6. Right, so effectively, yeah, these quantization levels will be much closer together. And I'm just going to do a different color, because if we look at the problem now, let's say just here, right, using the using this one, right, the sampling resolution of 3. Well, the first one we can store here is 0. Okay, that's fine. But let's say we take another sample at this point, and let's just maybe mark, right, one sample here, right, another one. So let's say, you know, this is our sampling rate. Okay, how often we're taking samples. Now, if we say this one, well, this one is actually okay. I mean, this is, you know, approximately 1, that's fine. But then, like, I mean, let's say, for example, this one, well, really, this is kind of like 1.8. But, of course, we can't store 1.8, okay? We have to actually go up and store this as 2. Same as the next one, okay? We're also storing this as 2. Right, this one, I mean, this is kind of like a 1.5 or maybe sort of 1.4. So yeah, here we're actually going to have to store this as 1, and then I guess this one, I mean, this is like a sort of minus 0.3 or something, so here we'd have to store it as 0. And then if we actually look at this, so let's just try and draw this here. Okay. So effectively, you can see, well, obviously the blue wave, this is the original analog signal, whereas this orange wave, I mean, this is the actual sort of digitized or quantized sound sample that we've actually like stored and saved in the computer. And obviously, you can see here, right, these are not that close, right? They're not that accurate. And I've actually got a nice diagram here. So I mean, well, here they call it bit depth, but the bit depth, right, is also sampling resolution. You know, it's the same thing, just different name. So here we've got, you know, sort of a low sampling resolution. Okay, we've also got a low sampling rate. Right, so the sampling rate, this is, I mean, this is how many samples you take every second. Right, so in this case, both of them are low. So this gives us a large error when we actually digitize or quantize the sound sample right into a, you know, digital form. But then obviously if we increase it, so if we increase the sampling resolution, right, and sampling frequency or sampling rate, right, then it gets more accurate. Then of course, yeah, increasing them even higher, well, then it's going to get even more accurate. All right, and I mean, yeah, I think this diagram is quite nice. You know, hopefully this explains it quite well. So in order to actually put that into words, because yeah, sometimes that's the most difficult thing. You know, sort of from the diagram it's quite easy, but yeah, actually explaining it can be a little bit harder. So let's say maybe a higher sampling resolution, right? This will mean we have more distinct, let's say more distinct quantization levels. Yeah, let's say, right, more distinct, right, yeah, quantization, and I think that's how you spell it. Quantization levels that, yeah, I know that can be represented. Okay, right, let's say, right, this means, so what this means is that basically the difference between the sort of each amplitude is going to be less. Because, for example, like maybe here, let's say this 0, I don't know, this, I mean, I don't know, let's say this represents, well, just like 0 decibels or something. Maybe this is like 10 decibels, 20 decibels, 30 decibels. well, of course, if we want to store 22 decibels, right, we've got to round down to 20. Whereas if we're storing, you know, sort of like 20, then 20.1, 20.2, 20.3, 20.4, of course, you know, it's going to be more accurate. Right, so let's say, yeah, this means the, let's say the difference, maybe the difference between I don't know, let's say the amplitude, I don't know, yeah, let's say the difference between the amplitude values that we can store, can store will be smaller. Right, and let's say hence, right, hence the difference between the actual original analog, right, hence the difference between the between the original analog, right, amplitude, right, let's say amplitude / wave, will be less. Yeah, so this means the difference. I mean, yeah, I think the grammar is kind of terrible on this. It's, you know, pretty bad explanation, to be honest. Right, hence the difference between the original analog's amplitude wave will be less. Yeah, I mean, I don't know, right? Honestly, I mean, you could probably explain that better. Like, I think it's got the key points, but yeah, in terms of the grammar, you know, the sentence structure is sort of terrible. But again, I mean, hopefully the diagram explains it, right, better than, you know, that paragraph does. Right, the next one, so give one other way that the accuracy of a sound recording can be improved. So as we saw, well, either we have, you know, sort of more quantization levels, right, so by increasing the sampling resolution, or we can actually just, you know, increase the amount of samples we take, right, so that's going to be the sampling frequency or sampling rate. And here it just says give, right, so we don't need to explain, I mean, it doesn't say explain, doesn't say describe. So let's just say, right, increase, right, increase the, sampling resolution, right, sampling rate. And again, so right, sampling rate and sampling frequency, they're the same. Sampling resolution and bit rate, right, they're also the same. Also, bit depth, right, not bit rate. Right, the next one, a computer has a central processing unit, CPU. The CPU includes the registers, right, program counter, PC, memory address register, MAR, the memory data register, MDR, the accumulator, ACC, and current instruction register, CIR. The table contains 5 statements about the role of registers in the fetch-decode-execute cycle of a CPU. And then I'm going to read the instructions. It says 2 of the statements are not correct. Identify the letter of each incorrect statement and suggest a corrected statement for each. So again, I'm going to do what I did before. I'm going to read them. I'm going to mark the ones which are sort of definitely correct, definitely incorrect, and then the ones I'm unsure about. So right, let's say the first one, the PC stores the address of the next instruction to be accessed. I mean, I think that seems true. Right, the MAR stores the instructions of the program that's running. I mean, this one is going to be false because, well, the MAR, right, is the address register. So it's going to store the address. And we can say, well, it's the address of the current instruction, you know, this is sort of being executed, right? During the execute stage, it's also going to be the address that we're either reading from or writing to. Right, the MDR stores the data passed to it from the PC. I mean, this is also not true. Because if we think, well, the address in the program counter is copied into the MAR, but the MDR, I mean, well, this is going to store data, but it's the data that we've just sort of read from memory, right? Or the data that we're reading. Or the data that we're writing to memory. So right, that's going to be false. And again, it does say only 2, but I mean, let's just check that these are true. Check we've not made any mistakes. Right, ACC stores the result of each calculation. I mean, that should be true. CIR stores the instruction currently being executed. That seems true. Right, I mean, so if we go here, right, the incorrect statement 1, that's going to be B. Right, incorrect statement 2 is going to be C. And then if we actually write a definition for these, write a corrected version. Right, so for B, I think what we can say, maybe during the fetch stage, right, the MAR, that's going to hold the address of the current instruction being executed. Right, and then let's also give a sort of more detailed explanation. So let's say during execution stage, right, then what this will do, it will store the address, again, that's about to be written to, or the address that's going to be read from. Right, the MAR stores the address about to be, let's say, read from / written to. Yeah, I think that's fine. And then for C, right, the MDR stores the data passed to it from the PC. So, I mean, let's just use the same format. So we go during the fetch stage, right, the MDR, right, stores the current instruction, right, current instruction about to be executed. And I mean, basically, well, this instruction is stored in the address that's contained in the MAR. So if the MAR has the value 5, well, that means the instruction is stored in address 5. And I mean, this is not really required, but sometimes you do see this register transfer notation. And I mean, this is more for A level, really. But so what we do is we say, right, MAR like this. And when we have these two brackets, what this is saying is, well, one bracket means the contents. So here we're saying the contents of the MAR, right? So let's say that's 5. But then we have another pair of brackets. So that's saying, well, the contents of, that data. So if the MAR is 5, right, okay, yeah, that means the contents of the MAR is 5. But then we want the contents of address 5, right? So that's what's copied into the MAR. Yeah, I mean, so maybe that makes sense, or maybe it doesn't. But I mean, that's just the register transfer notation. Right, okay, and then let's also say, right, during the, let's say, execution stage. Yeah, I think I won't worry about spelling. Right, during the execution stage, the MDR. And, okay, let's say, right, this stores the data that's just been read, right, or the data that's, written to memory. Where the MDR stores the data, maybe just read from memory, right, or that's about to be written to memory. Yeah, I think that makes sense. Right, the next one, the computer has a single core 3.5 gigahertz processor and an 8 kilobyte cache. State what is meant by a 3.5 gigahertz processor. So, I mean, giga, this means billion. So what this is saying, well, basically the, the sort of system clock is going to tick, right, 3.5 billion times every second. And on each clock tick, one instruction will execute. Okay, so if we combine that, what we can say, right, that, let's say, the system clock will tick 3.5 billion times per second, right, hence 3.5 billion instructions can be executed per second. Yeah, I mean, this is technically not true because, I mean, some instructions take multiple clock cycles, but basically, I mean, you're going to do 3.5 billion fetches per second, you do 3.5 billion decodes per second, and yeah, 3.5 billion executes per second. All right, because again, on each clock tick, each stage of the fetch-decode-execute cycle will happen. But yeah, I mean, I think this is good enough, right, for a simple definition. Right, the CPU is changed to a dual-core 3.5 GHz processor. Explain how the number of cores affects the performance of a CPU. So, I mean, basically, like, if it's dual-core, you can kind of think of it as, like, rather than having one person doing something, you just have two people doing something. And obviously, well, they can work on different things, at the same time. Okay, so what you're going to get is you're going to get simultaneous execution of instructions, right, or also, parallel execution. So, right, let's say, okay, right, let's click the text again. I know maybe each core can operate independently. Yeah, right, each core can operate independently, and again, yeah, who cares about the spelling? Right, hence, I mean, well, let's just say, you know, multiple instructions. Yeah, okay, let's say multiple instructions can be executed, you know, at the same time or simultaneously. You know, let's say providing, yeah, let's say parallelism. And again, yes, spelling, don't worry. Right, hence providing parallelism. Yeah, that seems okay. And then, I mean, let's sort of make it more kind of specific to this example where they say dual core. So, for example, a dual core CPU, right, can execute, right, 2 instructions at the same time. Yeah, so I think that's fine. Right here, the amount of cache is increased to 64 kilobytes. Explain how the amount of cache affects the performance of a computer. Now, this one I actually have I have another diagram here which I just got. So what we see, okay, hang on, that's selected on the eraser. Let's go. Yeah, I think that one seems okay. Right, okay, what we see then, we have multiple cores, right? So this here is core 1. Right, of course, you know, we can have core 2, core 3. I mean, yeah, here they call it core n, right? Many cores. And then each core is going to have its own cache. So here we see this level 1 cache, right? Then we see level 2 cache, right? Also, in level 3, which is going to be bigger. I mean, basically, so cache is going to be, you know, sort of small but fast access memory. And cache is actually going to be SRAM. I think maybe SRAM is possibly not included in the new syllabus. Okay, let's write that again. Yeah, okay, SRAM, right, so SRAM is going to be faster, but it's, you know, sort of more expensive. Also, it's going to take up more physical space, like per sort of unit of data. So effectively, let's say you want like 1 megabyte of SRAM. Well, I don't know, maybe that's like, you know, 1 centimeter squared. But let's say here, if we want, you know, 1 megabyte of DRAM, well, maybe this is like 0.5 centimeters squared. Yeah, I mean, so that's the thing, right? So SRAM is just going to be faster, more expensive, but the physical size per unit memory is also going to be bigger. But you know, for the processor, well, we don't really care about the cost. We don't really care about, you know, the sort of size that much. We just want, you know, fast access. So that's why we have this, well, level 1, level 2, level 3 cache. And we can see level 1 is about 100 times faster than RAM. Level 2 is, well, 25 times faster. And I mean, level 3, I'm not sure, maybe 10 times faster. You know, obviously this depends on specific hardware, right, specific systems. But yeah, just, you know, kind of estimates. So, I mean, the whole point of the cache is, well, it's going to store the frequently accessed instructions, and frequently accessed data. So let's imagine we have, I don't know, some function which we're calling like 1 million times, because maybe this function is in a loop. Yeah, or it could be, I don't know, maybe it's a game, and this game is updating, you know, 30 FPS, right, 30 frames per second. So of course, you know, we're constantly calling this function, right, over and over again. Now, if we had to fetch it from main memory every single time, well, as we can see, right, that's going to be 100 times slower. So what we want to do is these frequently used instructions, right, frequently used data, like maybe we have some array and we're just like looping through constantly, you know, sort of accessing this array or something. You know, this frequently used data and instructions we want to store in the cache, because one, I mean, well, SRAM is just faster than DRAM, right, but it's also the physical distance. Because, like, let's say the physical distance from, say, the L1 cache, right, to the CPU components, right, so, you know, the control unit, the accumulator, you know, the other, say, the registers, right, I mean, this might be, like, I don't know, maybe this is, like, 1 centimeter, right, this physical distance. Whereas if we look here from, okay, here we go. from this thing to main memory. Like maybe this is, I don't know, 20 centimeters. And you've got to think, right, when you're doing instructions like 3.5 billion times per second, as according to that previous question, based on the clock speed, then like this physical distance does actually matter, because of course, we're doing it right 3.5 billion times a second. So that, the time for the electrical signals to travel, will actually have an impact. So effectively, I mean, if we go back and try and answer this question, well, the reason we want more cache is because then we can store, more frequently accessed instructions and data in the cache, which means that, we kind of less often have to go to RAM. And, having to go to RAM because it's not in the cache, right, the word for that is a cache miss. So, yeah, we could include that if we want. Right. Okay, here we go. I mean, first, let's just explain why cache is useful, right? So, frequently used instructions / data, right, can be stored in the cache, or let's say cache. Right, this is fast. Let's say fast access. I mean, we can just say memory, right? SRAM. Let's say SRAM memory. I mean, even though, well, the M does stand for memory, but let's say memory, just so the examiner knows what, kind of knows that we know what it means. Right, okay, so this is fast access SRAM memory. Right, that is close. I mean, we can also say inside, right, close / inside the, let's say, CPU cores. Right, and then we can say the advantage, right, is that, I mean, again, well, let's say data / instructions, right, don't have to be, I mean, we can say fetched, right, or, read from, let's say read from / written to, right, main memory. Right, let's say main memory, that's RAM. And let's say, right, which is significantly slower. Right, and then let's say why. So this is kind of like what RAM, this is what cache is used for, and the advantage of cache. But then let's say specifically why it's an advantage to have more cache. Right, hence having more cache, right, means that we can, we can store more. We can store more. Right here, we can store more data more data / instructions in it. Right, hence, hence there will be less cache misses. Right, hence there will be less cache misses where we have to go to RAM to fetch the data. And again, I mean, it's probably not the best, like, grammatically, but I think as long as you can, like, spew out the main points, then that should be okay. Right, then it says the computer has both primary and secondary storage. Random access memory RAM is one example of primary storage. Right, describe what is meant by RAM. I mean, so the actual, random access, what this means is that the data can be accessed in the same time, no matter where it is on the physical device. Right, now this is in contrast to a hard drive. And I think, to be honest, let's just go here. Now, the new syllabus, they actually don't really require you to know, how these things work. Although it is probably good just to have a sort of basic understanding, right? Just so you know the advantage of, one over the other. Now, let's say we have a hard drive, and okay, here it is. It's really difficult to actually see the, dot on this thing. Right, okay, so let's say this is the actual platter, right, the disk, so the spinning disk of a hard drive. Right, and then a hard drive, you have this read-write head. So this read-write head, right, this is the thing which actually, well, again, that's going to read and write the data. Now, let's say, for example, the data is here. So what needs to happen is, well, first, right, this disk is spinning. So the disk is going to be spinning like this. But, this read and write head, this has to move. Okay, so of course, well, this movement is actually going to take time. Right, likewise, this spinning, okay, this also takes time. Now this one is going to be slower, right, to access compared to, I don't know, maybe like if the, let's say if the data was here. Oops, hang on. Right, I mean, let's say if the data was here. Yeah, wait, what was happening? Okay, yeah, I don't know, don't worry about that. Because, I mean, let's say if the data was here, well, now it only has to, rotate this distance, and also the read-write head only has to move a smaller distance too. Right, so this is the problem with a hard drive, that depending on the physical location of the data on the disk, right, it's going to take a different amount of time. Whereas if we have RAM, RAM is going to be a constant amount of time, regardless of where the data is on the actual device. So yeah, let's just explain that. So right, let's say random access. Random access means the data, right, can be accessed, let's say in the same amount of time, right, or in a constant time. Right, then say regardless of where the data is, right, and then yeah, let's say on the device. Alright, that's fine, and then, I mean, that's quite a specific point, right? Then they often just like some general points. So here we can say, well, RAM is volatile, which means when you turn off the power, the data is going to be lost. Right, RAM is also volatile, yeah, which means that when the power is turned off, yeah, all, I mean, I don't know, yeah, let's say all data in RAM will be lost. And let's also say, the common data you store in RAM. Okay, so let's say usually, well, I mean, yeah, let's just say RAM again. I say RAM is used to store the currently, let's say currently open or currently execute. I mean, let's say currently open, right, programs, and we can put in brackets instructions and data. Yeah, I think that's fine. Right, the next one, read-only memory ROM is another example of primary storage. ROM often stores the startup instructions of a computer. Identify one other item of data that is commonly stored in ROM. Right, so for this one, I mean, we can just say BIOS. Okay, that's always, stored in ROM. I think usually they would also accept firmware, and then sometimes like system settings. So maybe there's some system settings that, the manufacturer doesn't want the user to change, because if they change it, it's just going to, completely break the whole computer. Yeah, those system settings can also be in ROM, right, to prevent modification. Right, some computers make use of virtual memory. State the purpose of virtual memory. Now, this one is a bit difficult, but virtual memory, I mean, basically it's going to be like additional, well, alright, let's say when your RAM is full, then you can make use of virtual memory, which basically that's just using your secondary storage as temporary RAM. Right, so like on my computer, I've got 16 gigabytes of RAM, but then it says I've also got 24 gigabytes of virtual memory. Now, I'm actually not sure if that just means, well, is it like 8 extra gigabytes, like 16 gigabytes of RAM, right, plus 8 gigabytes of virtual memory, right, gives 24 total. Yeah, or maybe it's like, 16 RAM, 24 virtual memory, which gives 40 gigabytes total. I'm actually not sure of the specifics, but if you do want to find out for your particular computer, I mean, on Windows, if you just go like system information, yeah, open the system information program, right, then it will tell you. And of course, yeah, search on Google, right, you can also find out. So yeah, I mean, if we just write that as a definition, or well, the purpose. So let's say, right, if RAM becomes full, then I guess, well, let's say, yeah, right, let's say then secondary storage, right, can be used as, right, as temporary slash, yeah, I think temporary is fine. Right, let's say temporary memory, for programs slash data. Yeah, I mean, that seems okay. And then we can probably say that, yeah, I mean, well, let's say pages, right, because it's going to be a page of data. And when we say a page, I mean, usually that's just like 4 kilobytes of something. So it's kind of like a 4 kilobyte block of data. Right, so let's say pages can be swapped. So swapped means like moved from RAM into virtual memory, right, or moved from virtual memory into RAM. Right, so let's say, yeah, swapped in and out of virtual memory as required. Yeah, and I think that should be fine. And I mean, honestly, like maybe that's more, more detail than you need for 1 mark. But in the exam, it's always better to write more detail, right, rather than not enough detail. Because, well, maybe the examiner is, 50-50, right? Should I give you the mark? Should I not? Well, if you've got more detail, of course they're going to be more likely to give you the mark. Yeah, you're going to be more likely to hit those points. And I think also it just gives a good impression, if you're writing sort of short, like 3-word answers, I mean, maybe the examiner might think, well, either this student is sort of lazy, right, or they actually don't understand the content that well. Whereas, yeah, if you're given these, longer descriptive answers, then of course the examiner, they're going to have a good impression. And yeah, they're going to assume that you know what you're talking about. Right, the next one, a computer has an operating system OS. Complete the table by writing each missing OS function name and description. So managing memory, I mean, here we can say this is for sort of memory allocation. Right, so this is, yeah, let's say used to allocate memory, right, to specific processes. Right, specific processes as required. Right, okay, let's say also, so this will also ensure that 2 processes never have the same memory location. Yeah, or, alright, let's say also ensures that 2, yeah, let's say 2 processes, right, never have access to the same, right, memory, let's say memory address space, right, so basically the same memory locations. Let's say, right, this could cause problems. So basically, well, it could cause data corruption, right, maybe, or security vulnerabilities. Yeah, and I mean, this will be things like, sort of buffer overflow attacks, which, if you want to search that, yeah, you can type it. I say like buffer overflows. Again, that's not required, but maybe some people are interested, right, in searching that. Again, let's go more detail, right? Let's also say, yeah, all right, let's say memory management, right? This also handles, and then what we'll say, well, this handles virtual memory segmentation and paging. Right, virtual memory segmentation and paging. Now, if you don't know what those things are, there's actually a good video from this guy. I think his channel is literally just called Computer Science. Maybe search like Computer Science A-level, then just go, well, yeah, paging, paging, segmentation, virtual memory, right? If you search that on YouTube, right, he actually has a good, yeah, sort of good videos explaining this. Right, the next one I didn't know, so I did actually check in the mark scheme for this. I think here they, yeah, I think here they call it something like platform for running application software. Now, I'm not sure how specific you have to be. Like if you just said, I don't know, if you just said like an interface between the hardware and software, I'm not sure if they would accept that or if they want this specific term, platform for running application software. Because if you think the sort of levels of a computer or the layers, right? Well, at the bottom you've got the hardware, then on top of that you've got the firmware, right? Because, well, the firmware is software that kind of directly manages the hardware, or it can be things like drivers, right? So just this kind of low-level software, right? Then on top of that you've got the operating system, and the operating system also has multiple levels, right? The lowest level would be the kernel. And yeah, I can just write that, right, the kernel like this. And what the kernel is, that's going to be the sort of fundamental, yeah, let's say like the fundamental features kind of crucial for the system running, right? So things like, things like memory management, right? Things like file management. So, when you want to like create a new file, well, the kernel is going to have the code in order to, create files by, let's say, sort of, allocating space, right, updating. Updating the file system, so whether it's like FAT32, right, the file allocation table, I guess more modern, maybe like NTFS. Just updating all of those file records, right? It's also going to do things like, let's say, for example, handling Wi-Fi, right? So, managing the protocols, right? Bluetooth, all this kind of low-level stuff, right? On top of the kernel, then you'd have, for example, let's say the utility software, the application software. And then, and of course, some application software can be part of the operating system. For example, like Microsoft, Microsoft, you have the calculator, you have Paint, possibly you have Microsoft Office, on Windows. But then you also get like third-party application software. Of course, any other Office program or games or, web browsers, right? Just whatever. So I think that's what that's saying really. It's just, these different levels, and it's kind of like an interface between the hardware and, the application software. Right, so the next one, managing peripherals. Probably, one thing, right, is what's called like USB plug and play. And it's a strange name, but what this means is basically, well, you plug in the device and then the driver will be automatically installed. Right, so for example here, I've got this graphics tablet. Well, I didn't have to like go to some website, download some driver for this graphics tablet. Okay, I literally just plugged it in. Right, same as like a webcam or a mouse or a keyboard. You just plug it in and the drivers will automatically install. Now, of course, these days that's common, but I guess sort of in the past, right, that wasn't as common. And if you wanted to, right, if you wanted to connect a new peripheral, you'd actually have to download. You'd have to download the driver, right, or maybe the driver would come on some like CD or something. So let's not mention USB, but we'll just say maybe automatic installation. I know, maybe like allows automatic installation of device drivers. We can also probably say, let's say, right, manages. So manages communication, maybe error handling. Let's say like protocols, etc. Because, for example, the USB is a protocol, so the operating system has to understand the USB protocol, right? The the Ethernet protocol, stuff like this. I think that should be okay. You can also say it's going to store a list of kind of previously accessed or previously installed. I guess previously installed or let's say previously connected, right, peripherals. So maybe stores a list of previously, let's say previously connected, maybe peripheral devices, right, based on a file. I guess we can say like file descriptor or maybe device ID. And this I think right, because let's say, for example, you have a phone. Well, if you plug it in for the first time, it's probably going to install the device drivers, right, things like that. But then when you install it for the second time, it's actually going to recognize that device, okay, because you've previously connected it. That's going to be the same for any like graphics tablet, mouse, anything, right? So it's just going to recognize what devices you've already connected previously, because I guess probably it's going to save some settings associated with those devices. Then it says the OS handled interrupt, and we want to state the purpose of an interrupt. So here the purpose, let's say it's going to handle, it's going to maybe allow the CPU to handle, like a task, right, processes, right, of higher priority. And let's say, for example, maybe handling, right, hardware errors, let's say user input, right, swapping programs, right, etc. Right, identify one input device and one example of an interrupt that it can generate. So let's say the input device, could be mouse, keyboard. So let's go mouse. and the interrupt, I mean, we can just say like mouse click. Okay, and you know, of course, if it was a keyboard, well, we say, you know, like key pressed. Right, a processor is currently executing a program. The processor receives an interrupt. Explain how the processor manages the current program and the interrupt. Right, so this one is quite detailed. Let's try and draw a diagram for this. Yeah, I'm just going to undo all of these. Right, so what we have. Okay, where is that? Okay, here we go. Right, so let's say we've got a processor. Let's call it P1. Right, this is the current process, and I mean, well, this could be a game, it could be a web browser, it could be, you know, background task, anything. Right, let's say at this point here, there's going to be an interrupt. So I mean, let's call it interrupt. I mean, just I1. So what needs to happen then is, well, this P1, right, when there's an interrupt, like all of these values. All of the register values, they're going to be saved into RAM. And I think you can say, well, saved onto the stack, that's also okay. So right, let's say register values, and that's going to be saved into RAM. Right, then what's going to happen, I mean, well, this interrupt, okay, there's going to be a thing called ISR, right, this is interrupt service routine. Now the interrupt service routine, this is the code that executes for that particular interrupt. So let's say, you know, the user clicks the mouse. Well, the operating system has code every time the user clicks the mouse. And I guess that's going to be like, for example, detecting right where the mouse click was, detecting what the user clicked on. You know, of course, if they clicked on, let's say like an icon, well, then it's going to open that program, okay? So yeah, there's obviously just, you know, functions associated, there's code associated with each interrupt. So what's going to happen? I mean, let's say this interrupt has the memory address of like, I don't know, 1 million. Okay, yeah, I think that's 1 million. So what's going to happen then? Well, the memory address of this interrupt service routine is loaded into the program counter, right? And then it will just continue like fetch decode executing. Okay, so yeah, this interrupt service routine, this will execute, right? When this finally finishes, well then, I mean, right, this is why we saved the register contents into RAM. And when I say register, I mean this means, well, the program counter, the, you know, memory address register, MDR, CIR, right, also things like the status registers, right. So they were saved in RAM, right. They were, you know, sort of pushed onto the stack, right. So then what's going to happen? Well, these are then going to be loaded back. So let's say we got to, I don't know, maybe this was on the. Maybe here, you know, the program counter was 500, right? But then we had the interrupt. Well, now what's going to happen is the program counter is going to go back, and the program counter is going to be reset to 500. Okay, and yeah, when this is reset, well, then this can, you know, continue executing. And I mean, there are also other stages. For example, like when this interrupt service routine finishes, well, then it will check, has there been another interrupt? And if there's been another interrupt, well, then it will handle that interrupt. And of course, it will keep handling interrupts until there's no interrupts. And then, yeah, when there's no interrupts, right, well, that's when it's going to, you know, do this of like loading back, loading back the register values right into the registers. So yeah, that's going to be quite a long description, but let's see if we can do it. Right, so, right, let's say, yeah, when an interrupt occurs, right, let's say the OS will save the current register values. Alright, register values, register contents, right, into RAM. Right, you can also say onto the stack, right, that's probably more specific. Let's say onto the stack. And, you know, if you're talking about stacks, again, really, you should say push. Now, I mean, the whole thing, right, pushing data onto the stack, popping data from the stack, that's more of like a kind of A-level thing, to be honest. So yeah, I think just say save it in RAM. That's also fine. Let's say then the ISR. Let's actually write that. Let's say interrupt service routines. or in brackets, let's say ISI, right? Then the interrupt service routines start address, right, will be loaded into the PC, right, and the ISR will start to execute. Right, and I guess then we can say once the ISR is finished, right, once the ISR has finished executing, right, I guess for the OS, right, CPU, right, will check for new interrupts. Right, okay. Yeah, I guess I will check for new interrupts and their priority, maybe let's say. Because, you know, you can have high priority interrupts, low priority interrupts. Right, let's say it will then, I don't know, maybe it will then execute it will then execute these interrupts. Okay, right, in order of priority until there are no interrupts remaining. Right, let's say at this point, so this is where we want to load back the register values from the original process. Right, so at this point, the register values from the original process right, can be, right, I mean, well, you could say loaded from RAM, right, or we can say popped from the stack, right, and loaded, loaded back into the registers. Okay, and let's say like now, right, so now the original program, I mean, let's not say program actually, let's say process, right, now the original process, because the difference is, right, a program, well, that's just, you know, a program saved on your computer, but a process is like a running instance of that program. Because let's say you have, I don't know, I mean, let's say you have a like web browser, I mean, let's say like Google Chrome. Well, you know, you have, right, one instance of Google Chrome saved on your computer, right, so that's one program, but you might have like 3 different windows open. So in that case, you have like 3 processes for Google Chrome. And to be honest, you know, something like a web browser, actually, like each tab has a different process. They also have, you know, sort of background processes. And, you know, I guess like in Task Manager, you can see all of those, you know, running processes. But anyway, right, so now the original process can be resumed. Right, from the point, maybe from the same point as before the interrupt. Yeah, I mean, I think that should be enough. I mean, I think they also say, like, basically so yeah, when an interrupt occurs, I mean, the current instruction will finish executing first. So like, if, you know, if you're sort of halfway through executing the instruction and there's an interrupt, well, yeah, that instruction will finish executing. So I mean, let's write that. I know, maybe like, yeah, all instructions will finish. And I mean, like, honestly, you know, this should probably go near the top, to be honest. So let's actually just copy it. Right, when an interrupt occurs, the right, current instruction will finish executing. Right, and let's say then, yeah, then the operating system will push the current register values onto the stack. Yeah, again, I mean, it's, you know, not the clearest description, but I think that should be enough to get 5 marks, right, hopefully. Right, next one, a student enters a uniform resource locator URL into their web browser. Draw and annotate a diagram to show the process from the user entering the URL to the web browser displaying the web page. Now, I mean, this one is a bit weird because I think a lot of people thought they removed this from the syllabus, but I guess, yeah, here it shows they haven't. Right, I mean, so the best way to draw this, okay, there we go. So, I mean, we're going to have a client and server, right, because it's a client-server system. So, I mean, let's just start with drawing this. Let's say client. We can also say, I mean, let's say web browser. Right, and then this side we're going to have, well, the server, right, the web server. Yeah, and I mean, I suppose here, you know, I mean, how many marks is this? Right, 5. like we can probably also talk about DNS. So yeah, let me actually just erase that because I kind of want to move it down really. Yeah, I mean this diagram can get quite detailed, you know, if you want all of the information. Let's say here we have like a DNS server. Right, and then maybe down here we have the web server. Right, so the first thing we can do, I mean, you know, we can also add, I mean, let's say here we just add the router. Right, so what's going to happen first is, well, basically, you know, you need to convert the URL into the IP address. So we'll just say an example. And right, I mean, it does say annotate. So I'm actually just going to sort of number it. So let's say, right, user, yeah, I mean, so they've already entered. I mean, let's just write that again, right? User enters URL. Let's give an example, right? E.g., right, Google. All right, Google, yeah, .com. Right, so second, let's say that the URL, right, let's say translated, right, translated into IP, right, IP address, right, via DNS. And I'm actually going to go sort of like 2.1, 2.2. So let's say, right, first, I mean, basically, the web browser and operating system will have a list of, you know, IP addresses mapping to URLs. And if there's a match found there, well, then you can just stop. So first, let's say, right, browser, let's say browser and OS, right, checked, right, for DNS match. And you know, if that's found, well, then it can just stop because it's going to know the IP address of that website, right, or of that URL. Right, let's say 2.2, right, let's say if not found. Right, if not found, then let's say the sort of local router, right, let's say the local router and ISP, right, ISP's DNS server, right, maybe let's say checked for match. Yeah, I mean this is going to get super detailed, right, and then what if that's not found, right, then let's say, I mean again, right, let's say, right, if not found. Right, then, and I mean here you can say, well, the global DNS server, and what they actually call that, right? Right, I'm going to write it here because I think there's not enough space. Right, the global DNS server is called the authoritative. Yeah, right, so authoritative, right, let's say the authoritative name server, right, that's going to be like the global DNS server. And I think there's only about 13 of them in the entire world. I mean, I think that's what it says in the book, although, yeah, maybe now there might be more. All right, so, I mean, basically, it's going to use this method, right? So first it's going to check the browser and OS. If they don't know the IP address of this URL, right, then it's going to go to the sort of, you know, home router, right, or the sort of local router, yeah, maybe in the office or something. Right, if that doesn't know, well, then it's going to go to the ISP. Or let's say, yeah, ISP DNS server. So we can sort of, I don't know, maybe draw an arrow going to here, right, then it goes to the ISP, then it's going to go to the DNS. And, you know, we also want arrows going back. And you could mention that basically it's going to be cached. So if, for example, you have to go to the DNS, right, well, the authoritative DNS server, then the IP address that this returns is then going to be saved, right, or cached by the, you know, the ISP's DNS server, right. It's also going to be, you know, saved or cached, right, by the sort of the, you know, let's say the local router, right, and also by the web browser. And I mean that's only going to be cached for a certain amount of time. Like, I think a web browser only caches DNS records for about 60 seconds. And basically that's for security, because if you get some like malicious DNS record, well, you wouldn't want to save that for like an entire week, right? Because then you're going to be accessing, this malicious website for the entire week. Yeah, but I mean they will be cached for, a certain period of time. Right, so I guess that's DNS, right? Then when you actually know the IP address, well, then you can actually send the web request to the web server. So let's say, right, this will be the HTTP request. And of course, like in many cases, this is going to be HTTPS these days. Right, so what's going to happen? Well, the web server is going to, basically it's going to sort of look at this HTTP request. Right, it will look at things like the path, right, so which file you're requesting. It can also look at things like the session, and so the session in terms of, what session cookies you've sent, because that session cookie, let's say, I don't know, maybe session, right, path, based on the session cookie, that could correspond to, what you, let's say what account you're logged in as, maybe some sort of user settings. Right, so based on this, it's then going to have to generate different data, because let's say let's say you're on YouTube, and you're going to your video page, right? Your uploaded videos. Well, obviously, like the web server needs to sort of return different video contents, right? So different titles, different different sort of like counts, view counts, right? Based on the session, because the session corresponds to like what user is logged in. So there, here you could maybe mention some like database processing, like, because possibly you're requesting something from a database, and then when it's done that, well, then it's going to return to the browser, and the thing it's going to return is going to be HTML, right? It can also possibly return, for example, JavaScript, and then what you can say, right, the browser, and I guess really I need more space. You'd want to write sort of part 3, part 4, and again that can be about sending the HTTP request, maybe doing some database processing, right? Also generating the HTML, because the web browser has to generate the correct HTML, right? But then when you've done that, I'm just going to skip to 5. Let's say the browser. Right, browser, this will execute, right, so execute, let's say JavaScript, and again, this is lots of detail, right? It's going to execute JavaScript, right, and then also, right, render the HTML. So when we say render, what this means is, well, basically, take this HTML code and then actually like render it as a visible, sort of like a visible display to the user, because the HTML, this might include text, images, videos, audio, and then the browser is just going to convert this code into something the user can actually like see, click on, scroll around, right, stuff like that. Right, the next one. So complete the description of digital currencies using the terms provided. Right, a digital currency that does not exist. Right, something it can be only accessed electronically. So I think this will be physically. And here they have physically. Right, so let's just write that. Right, the next one. Some digital currencies have digital ledgers called, right, and I think that would be blockchains. And they have blockchains here. Right, these are decentralized databases where each transaction is stored as a new set of data with a something and is linked to the previous set of data. Right, so I think, here they like to say timestamp. Okay. Right, and this means that transactions cannot be altered. Hang on, so, because, the thing is, this can also be a hash value, but I noticed that hash value is not listed here anywhere. So I think timestamp should be okay. Right, okay, so transactions cannot be altered, only new transactions added, which allows the location of the data. Right, and that's probably, decentralized, okay, which, they also have here. Right, so, right, decentralized. And I think, again, I mean, blockchains are quite difficult to understand, so I do actually have this here. So if we look at this example, well, here we've got block 1. Okay, sorry, yeah, actually block 0. Right, block 0, which they call the genesis block. And I mean, you know, some of this, like the index, we don't really need. Like, I guess the index is just saying, well, this is block 0, right, this is block 1. Right, here they've also got the timestamp. Right, then we've got the previous hash. Okay, we've also got the current hash. And then we've got the data. And I mean, if this is financial, like a financial blockchain, you know, for example, like Bitcoin or, you know, some cryptocurrency, then I mean, this data will this will be about, you know, the sort of transactions, right? So this could be maybe like the sending address, the receiving address, the amount. All right, now that's going to be for Bitcoin, where, you know, all of that data is stored in the blockchain. Okay, I mean, there's also other cryptocurrencies where they actually don't store that. It's going to be more private. But, you know, equally, this blockchain could be about, I don't know, I mean, obviously you see blockchains for sort of NFTs and stuff like that, where there's not really, I mean, it's not really a financial blockchain. You know, that's obviously going to store other data. But anyway, I mean, the way this works as well, it's going to calculate a hash value based on this data. So, I mean, let's say our data is just like, I don't know, you know, ABC. And again, obviously this data, it could be, you know, financial transactions, like maybe it's 1 megabyte of data, right? Who knows? Now, when this data is hashed, well, maybe this hashes to the value, I don't know, like x1, you know, like hash, right? I mean, who knows what it hashes to? I mean, probably not something like that. Let's go, for example, B. Right, so yeah, here is the input data, right? It's then going to hash to this. And the thing is with this hash, right, this is a one-way function. So if we know this x1b, well, there's actually not really an efficient method for us to actually go back to determine the original data, right? And this is why it's secure, because, right, you can take this original data and then you can validate that it hashes to the correct value. But someone who knows the hash can't go back to, you know, kind of decipher the original data. And of course, like, let's say this changes. Well, let's say if we go, you know, A, B, like, let's say D, well, now this hash value is going to completely change. Like, maybe it's, I don't know, maybe we have like 4 and then T and then, let's say A or something. Right, so like just changing the original input data by a small amount is going to completely change the hash value. So yeah, this is why it's secure, because, right, if someone goes back, let's say, to like actually modify this data, well, then it means the hash value is going to be incorrect. So everyone else on the network is going to know that someone has modified the data, because of course, you know, now their hash values don't match up. Yeah, so that's kind of why it's secure. Yeah, okay. Alright, so I thought maybe there was a question about explaining this, but it seems not. Right, the next one, a self-driving tractor sows seeds and harvests crops for a farmer. The self-driving tractor moves automatically through the field, turning each end and stopping when it is finished. Okay, one reason why the self-driving tractor is a robot is because it has a mechanical structure that includes wheels, an engine and a framework. Right, give one other reason why the self-driving tractor is an example of a robot. So I think here we can say, right, let's say, yeah, it's also maybe, yeah, programmable. And here it just says 1, right? Yeah, okay, so it's also programmable, right, hence, right, can perform, yeah, tasks that the, I don't know, yeah, that the developer intends, yeah, it to perform. I think that's fine. Right, you can also, I think for a robot, you can also say it contains kind of electronic parts. Right, that should also be good enough. And then you can probably give some examples of those electronic parts, you know, like actuators, motors, sensors, right, etc. Right, if a person is detected within 3 meters whilst the tractor is moving, the self-driving tractor must stop. Explain how an infrared sensor, microprocessor and actuator can be used to stop the self-driving tractor if a person is detected within 3 meters. Right, now, I think first, I mean, let's just talk about what an actuator is, because I think a lot of people don't know. Right, an actuator, I mean, basically you can say it's going to be a mechanical structure that just basically it causes something else to sort of move or stop. So let's say this rotary one, I mean, I guess this can be used like to open a valve or something, whereas this linear one, I mean, this can be used, let's say, to move like a robot, or yeah, to like open a door, something like that. And, you know, I've got a common example here, like let's say on a bus or maybe in an office, right, to open the door, right, and also close the door. You know, you have this thing here, which is the actuator, yeah, obviously used to, you know, control the door. Right, so, I mean, so if we think about infrared, well, this can be an active infrared sensor. When we say active, this means it's actually going to send out a signal. Now, if you have a passive sensor, right, that's just going to be listening for, you know, other data. But I mean, what this will do, and I mean, let's go back. Yeah, let's go back and just draw this. Right, so yeah, it says what if it's too close to a person, right? So let's say here, this is the tractor, right, the infrared sensor. Right here is just going to be the person. So this is going to send out an infrared signal. Okay, it's then going to hit the person, right? Then it's going to be reflected back. And basically this, you know, the time it takes for sending out the signal and for it to be reflected back, okay, that can be used to, you know, determine the distance. So yeah, we just want to explain that. Right, let's say maybe the active infrared, right? The active infrared sensor will emit an infrared signal, or maybe an infrared beam. Right, the time taken for this beam to be reflected back. Right, reflected back and detected by the by the sensor, right, can be used to determine the distance, right, yeah, of the tractor, to this object. Right, so yeah, I mean, I guess you say, well, this data is sent to the microprocessor, right, and I guess you say, well, if the time is too short, right, if the time is too short or too low, right, well, then it will realize that it's too close. So, I mean, right, let's say, I guess that, right, then it means the object is too close. Right, hence a signal. So, well, then you want a signal sent to the, I mean, you can say, well, a signal will be sent to the actuator, which can be used to, you know, like turn on the brakes. I think maybe we also want to mention something about like a digital to analog converter, analog to digital converter. So yeah, right, the time taken for this being reflected back and detected by the sensor can be used to determine the distance of the tractor to the object. Yeah, okay, I mean, maybe here we can mention this. So let's say, right, this data is converted to digital. Right, so yeah, this data is converted to digital. Right, using so that's going to be an ADC. Right, so, and then let's just write that, so analog to digital converter. Right, yeah, and sent to the microprocessor. Right, if the time is too short, then it means the object is too close. Right, yeah, hence a signal can be sent. Right, so this will then be sent to the DAC. Let's say, right, digital to analog converter. Right, hence signal can be sent to the DAC. I know, maybe, and forwarded, right, to the actuator. Right, this, let's say, right, this is used to turn on the brakes. Okay, right, turn on the brakes, right, in order to stop the tractor. yeah, in order to stop the tractor, you know, before it hits the person or something. Right, I mean, I think, yeah, that should be good enough, hopefully. Right, identify one other sensor the self-driving tractor might use and how it will use the sensor. Right, so here, I mean, the sensor, I mean, I think one is, well, proximity, but proximity sensor, I mean, that's kind of the same as infrared, because again, you're just using that to measure the distance. Yeah, I think, I mean, maybe an accelerometer, because that can be used, you know, to measure the speed, things like the rotation, because I guess, I mean, you don't want it going too fast, right? So maybe accelerometer. Right, so maybe, yeah, maybe that's how you spell it. You know, honestly, my spelling is terrible, to be honest. Right, and then the use of this, let's say to measure, right, the speed / rotation of an object. And let's just say, you know, hence ensuring the tractor, right, is moving / at a safe speed. Right, and also maybe ensure it's not tilting too much. Right, ensure it's not tilting too much. And I guess, yeah, that's to, you know, prevent it toppling. Because I don't know, maybe you have some, you know, like steep bank or something, and of course, what if the bank is too steep, well, then you're not going to want to go up that bank. Yeah, so I think that should be okay. Right, explain the drawbacks of a farmer using self-driving tractors to sow seeds and harvest crops. I mean here, right, probably I won't list the whole description because, you know, I think the video is going too long, but probably here you can say, I mean, one, well, there's going to be maintenance costs. Right, you think you've also got, you know, expertise required, so maybe expertise, right, to manage / change, maybe, you know, update system. I mean, this is similar to maintenance, really. Right, you can also talk about social issues, so I don't know, maybe, yeah, local farmers will lose jobs. Yeah, lose jobs, you know, since they've been replaced by self-driving tractor. And then you can also maybe talk about safety issues. Right, let's say, right, could be unsafe if the tractor malfunctions. Right, if the tractor malfunctions, yeah, sort of / becomes unresponsive. Yeah, so that's some sort of, you know, killer tractor just like sort of running rampage. Maybe, yeah, I don't know, maybe it sort of goes out of the specified bounds, because a lot of these things, they're actually going to be programmed by GPS, right, to only actually operate within a certain, you know, GPS kind of, yeah, like GPS area. And if for some reason that stops working, well, maybe then they would, you know, start like driving into the chickens or something. Just, yeah, like running over all these animals, right? Maybe they run into a house, run into a barn. Yeah, I mean, who knows? Then it says the self-driving tractor has an inbuilt expert system that the farmer can use to solve any errors with the tractor. And we want to identify 3 components of an expert system. So the first one is just going to be an interface, right? And this interface, well, it just allows the human to, you know, communicate with the expert system. And this could be a CLI, right, command line interface. It could also be a GUI, right, graphical user interface. The next one, well, then we're just going to have the knowledge base. And the knowledge base, this will be all of the facts about that expert system. And I think the example in the sort of, you know, GCSE book is actually quite good, because they have an example of classifying animals. So let's say you have a dog. Well, some facts about a dog, you can say it's got 4 legs, it's got fur. I guess it sort of can swim. I mean, well, some dogs can swim. You know, obviously they can't fly. I guess they can't really climb. You know, just like all of these facts. Right? Yeah, I guess a dog would be a mammal, right? And then obviously, yeah, you've got different facts for different animals, right? Then what you're going to have is you have a list of rules. So let's say a rules base, and this can be, for example, well, is it a mammal, right? Yes or no. And then if it's a mammal, you're going to go one route, down the tree. The next rule can be, I don't know, does it have 4 legs, right? The next one can be, yeah, does it swim, right? Can it fly? So this will basically just be a list of rules, right? You just keep asking it questions. And then, well, it's going to be the inference engine which is going to use this. So yeah, the inference engine uses the knowledge base, right? It uses the rules base in order to actually get the answer. And then the inference engine can also tell you like why it thinks this is the correct answer, because again, it is literally just traversing these rules. And it can also tell you the probability of sort of how correct it is. So it can say, well, yeah, maybe I'm 80% sure that this animal is a dog, or I'm like, yeah, sort of 90% sure that this email is spam or not spam, right? Something like that. And of course here we only need 3, okay, but this should be the 4. Yeah, just in case you forget one. Right, then it says at the end of each day the self-driving tractor transmits the data it's collected to the farmer's computer in their house. The transmission uses an echo check. Describe the role of the self-driving tractor and the farmer's computer in the echo check. Yeah, so this, like, maybe I'll just mention that the tractor will communicate, probably by satellite, like the mobile network, because probably it's not going to have access to Wi-Fi, if it's on the middle of a farm. Right, and yeah, let's just plug in, as you probably saw. Okay, so let's say the tractor, the tractor sends, let's say, I don't know, maybe let's say sends the data via satellite, to the, I don't know, to the farm's computer. Right, you then say the farm's computer. The farm's computer then checks. I guess you say, yeah, the farm's computer then resends that data. Right, so yeah, that then resends that data to the tractor. And if the data is the same, well, then it knows the transmission is successful. Right, okay, let's say if the tractor receives the same data that is sent, right, then it knows the transmission was successful. Was successful and can transmit a success message to the farmer. Let's say if the data received was different, right, then it knows the transmission. The transmission was unsuccessful. I'm going to ignore that spelling. Unsuccessful, hence can resend the data. Let's say hence can resend the data or send an error message. And then probably we can say, this, let's say this process can continue, until the tractor gets, until the tractor receives the correct data from the farmer, from the farmer's computer. Yeah, I think that should be okay. Right, the next one, another method of error checking is parity block checks. The table shows 7 bytes that are transmitted using odd parity. The parity bit is being completed for each byte. Complete the parity byte for the data. Okay, so here then what we want to do, and let's select this drawer again. We just want to go down the columns and we want to count how many ones there are. And in this case, we're using odd parity. So that means the total number of ones has to be odd, okay? So here we've got 1, 1, then 2, then 3, then 4. So because we've got 4 ones, well, the parity byte then has to be a 1, in order to make there 5 ones in this column. And that means about 5 in total, right? So yeah, 5 is obviously an odd number. Right, the next one, so bit 7. Right, we've got 1, 2, 3, 4, 5. So here we've got 5 ones. Okay, so 5 is already odd. So in this case, right, this will just be 0. The next one we've got 1, 1, right, so that's going to be 0. Right, again, we've also got 1, right, that's going to be 0. Right, here we've got 4 ones, so we need an extra 1 in order to make it odd. Right, then we've got 5 ones, that can be 0. Then we've got 4 ones, that can be 1. And 3 ones, right, that can be 0. Yeah, that should be correct. Hopefully I've made no silly mistakes. And I would say, with a question like this, I mean, it is quite easy to make a mistake, so probably double check your answer. Right, data is transmitted using the internet. The data is encrypted before transmission. State the purpose of encrypting data. Now, some people here, they say, let's say, I don't know, maybe the data can't be hacked or something. Now, that's not true. A hacker can still hack the data, right? They can still, access the data without permission. However, the problem is if they access the data, well, the data will be in a form that they're kind of not able to understand, right? So that's the thing. Let's say, yeah, I'm going to move it down. What do they say? Right, state the purpose of encrypting data. Right, let's say if intercepted. Right, if intercepted / accessed, right, by an unauthorized party. Right, okay, yeah, unauthorized. Right, unauthorized party. Then they won't be able to understand the data, or they won't. Yeah, they won't be able. Right, let's say they won't be able to, right, understand / decrypt. Right, the data. Right, decrypt the data. I mean, or we could say, right, the ciphertext, right, back into the original plaintext. And again, it's good to use these specific words because, I mean, sometimes they do require, that you do say ciphertext, plaintext. Right, then we want to describe the differences between symmetric and asymmetric encryption. So again, I mean, I'm not going to write down a whole paragraph, although in the exam, right, in the exam, you should definitely be writing paragraphs. So here then, let's just say symmetric. Well, let's say the feature of this is going to use, let's say, a single / shared private key, which is used for encryption and decryption. Right, we say, right, so this private key somehow has to be distributed. I mean, this one is kind of the same as the first point, but I mean, this is kind of the disadvantage of symmetric encryption, that somehow you have to actually distribute this private key, without anyone intercepting it. Maybe where it has to be securely distributed to both parties. And we can also say, I mean, symmetric encryption is fast, right? This is the advantage. It's going to be fast, right? It also, let's say, also operates on large amounts of data. Yeah, or let's say, right, since the key length can be long. Right, in contrast then, asymmetric. Right, and again, I mean, the spelling, of course, well, you can just, yeah, have a look here. Right, I guess just one S. Right, so here then we're going to have, a different public key and private key. So right, let's say maybe each party has their own, right, their own public and private key. So right, that's going to be 4 keys for two-way, right, two-way communication. So what's going to happen? I mean, let's use A and B. So right, let's say person A, or we could use Alice and Bob. I mean, yeah, all right, let's go Alice and Bob. I mean, that's always used in encryption. Right, so Alice, she's going to use Bob's public key in order to encrypt. Right, so she uses Bob's public key to encrypt. Right, she can then right, she can send this message to Bob. Right, and then let's say Bob will use his private key to decrypt. Yeah, I mean, I think that, I mean, that's kind of how it works. Let's say, right, let's say it's more secure. Right, so it's more secure than symmetric. Right, more secure than symmetric encryption. Right, however, it's going to be slower, and I mean, you can also say it doesn't operate on as big data because, you know, the keys are going to be shorter. Right, and yeah, also can't operate right on as much data. Right, since the since the keys are shorter. Right, so I think, yeah, that should be okay. Then it says the data is transmitted using packet switching. Identify 2 items contained in the packet header. So, I mean, this one, well, we let's just say source IP. Right, so source IP, and when we say source IP, like this is our IP, right, the IP of the sender. Right, then we also say the destination IP. And I was actually thinking, would they include that, you know, because they're both IP addresses, like would they include that as just one item? But in the mark scheme I did check, okay, they do consider these as 2 different items. The mark scheme, they do also have the packet number as well, which I'll talk about. Now, some people think, well, why do we need to include the source IP? Because if you think about it, right, if you're sending data, like let's say to a web server, right, I don't know, again, let's say you go to Google, so you're saying, well, you know, give me the Google homepage. Well, the thing is, okay, that request goes to Google, but Google then needs to know who to actually send it back to. Okay, so yeah, that's why you have this source IP. Because, I mean, this is kind of like when people send a letter, right? If you send a letter, well, sometimes you also put the return address, because, yeah, if the person needs to send it back to you, of course, they need to know the return address of where to send it to. Now, the things like the packet number, I mean, this is really just used in TCP, right, not sort of UDP. And the reason for this is, well, if you're using packet switching, right, the data can arrive out of order, right, or the packets can arrive out of order because, you know, they can travel different routes, right. Also, maybe some packets don't arrive because, I don't know, there's some error, or yeah, some, you know, some problem. So what you need the packet number for is, one is to reorder the data into the correct order, because if you get the packets in, you know, like 3, 1, 2, well, of course you need to reorder that into, you know, packet 1, 2, 3. And then also, let's say you get packets 1 and 3, but you don't get packets 2. Well, basically then, you know, then you need to ask for packet 2 to be resent, basically. So yeah, that's the 2 purposes of the packet number. Right, then the next one, we want to give the purpose of a router in the packet switching process. So, I mean, the router basically is just going to forward the data onto the next hop. Because if we just draw this, let's say we've got, I mean, let's call it sender, right? Then we've got the receiver. Well, in here, maybe this is a router, this is a router, this is a router, right? Another router. So, I mean, the sender, they're going to send it to one router. Right, this router is then going to send it to another router, so maybe this one, right, and you know, this router then sends it to the receiver. But of course, I don't know, like maybe this router is not working, so in that case, well, maybe this router then sends it to this one, you know, this one sends it to this one, maybe this one sends it to, sends it to this one, right, then sends it, you know, to the receiver. So, I mean, basically, yeah, that's basically the purpose of a router. And the way it's going to do that is, well, it's going to use its routing table. So the routing table just has a list of basically IP ranges. And that can be like if you have an IP in the range of sort of, you know, 100, right, to 105, well, then maybe it means it should send it, for example, to, you know, this router down here. Whereas if it has an IP in the range, you know, 106 to 110, right, maybe it will send it to another router up here. And you know, when I say like IP address 100, I mean like, you know, 100, right, .000, to 105, you know, .000. Right, so let's say here then, give the purpose of a router. That's going to be, right, routers are used to forward packets, right, onto the next hop. And when we say next hop, well, you know, the next hop is just the router or the, I don't know, maybe the switch or the device. Right, so they're used to forward packets onto the next hop, right, based on the, let's say, information, right, in the routers, right, and then routing table. Yeah, I think that should be okay. Right, I think the last question, yeah, okay. Right, so a hexadecimal can be used to represent binary numbers. Convert the denary number 236 into hexadecimal. Now, this one, I mean, you know, in the exam you don't get a calculator, okay, so you do need to do this in your head. If we think then, well, the first one is going to be 16 to the power of 0, okay, which is just 1. Right, the next position is going to be 16 to the power of 1, which is 16. Right, the next one's 16 to the power of 2, right, 256. Now, here then, well, 236, okay, there's not going to be any 256. So yeah, we can just ignore that. Right, so we need to think, well, how many 16s go into 236? Now, if you have a good way of doing, you know, division, right, you can do that. However, I actually don't know any way to do division on paper. So yeah, I'm just going to sort of do it in my head. Right, if we think, well, 10 16s is 160. If we have 15 16s, well, 15 16s is going to be 240, right, because, yeah, 160 plus 80. So that means, well, there's going to have to be 14 16s, right, and 14 in hexadecimal, that's going to be E. And then we want to think how many we have remaining. Right, so if we, well, again, right, 16 times 15 is 240. So 16 times 14 is going to be 224. Okay, so that's going to give us 12 remaining. Because again, we've got, 236, right, and then, well, minus 16 times 14. And again, this is 224. Right, so yeah, this is going to give us 12 remaining. So then we want to think there's 12 ones, and 12 in hexadecimal is going to be C. Right, so here then we can just, write EC, because if we remember, well, 10 is A, right, B is 11, yes, C is 12, and then, right, F is going to be 15, right, F is, the biggest. But again, our answer, right, EC. Right, so give one benefit of using hexadecimal instead of binary. Let's type this. So what we can say is going to use, let's say, use less physical space. All right, physical space on screen. Yeah, you don't really want to say less space, because if you say less space, right, that could mean in terms of memory. But yeah, this is right. Let's say use less physical space on screen / paper. You can also say, right, easier for humans to understand. And actually, to be honest, I think, yeah, this is probably a better advantage, right, if you're just listing one. Yeah, I guess they would probably be the main two. So yeah, I'd probably go easier for humans to understand, right, as being the main one. Right, then it says 2's complement can be used to represent positive and negative binary integers. Convert the 2's complement integer, right, this, into denary. Right, show all of your working. So let's just write this out. Okay, we'll write down the positional values, right? So 2's complement, the first number is going to be negative. Then we go 64, right, 32, yeah, 16, 8, right, 4, 2, 1. This one is going to be, yeah, let me just write it out. So what we want to think, well, this is going to be, right, minus 128, right, plus 32, plus 16, right, then plus 4, plus 2, and plus 1. And I'm actually just going to simplify this, so I'm going to do the addition first. Right, so this is going to be 48, 52, 54, and 55. Yeah, I think that should be correct. So then we just have, what, minus 128 plus 55. And yeah, honestly, like, if you want, you could do this, using the sort of addition method on paper. I'm just going to sort of try it in my head. So right, if we go plus 5, well, that's going to be minus 123. If we go plus 50, that should be minus 73. And yeah, I'm just going to go, right, minus 73. and maybe I'll sort of highlight that just to show that's my answer. Right, then we want to convert 45 into 8-bit 2's complement. I mean, this one, it doesn't say, so we don't need to show our workings, right? So let's do it quickly. Right, there's going to be 0 minus 128, right, 0 64s. Right, there will be a 32. Right, there won't be a 16. Okay, right, there will be an 8, there will be a 4, there won't be a 2, though, and there will be a 1. Again, let's just do that again. So 32, right, then plus 8, that's 40. 44, and then 45. All right, that's fine. And I guess they do give us space for working. Right, then logical shifts that are performed on binary integers state the mathematical effect of a right shift of 4 places on positive binary integer. And I think here, right, they say positive because if we think, let's imagine we're just using 4 bits, I don't know, maybe this. Well, if we think, right, this is going to be minus 8. Now, let's say we just shift it 1 place to the right. Well, if we shift it 1 place to the right, we've got 0, right, then we've got 1, like this. Now, if we think this is now going to become positive 4, right, so if the number was negative, we can see, right, the sign will actually change. Now, I'm sure in assembly language, like they probably have instructions that will shift all the bits except for the, sign bit. Or they'll probably have, a shift that kind of, maintains the sign. But I mean, here we're just doing a simple logical shift. So this is why they say positive, okay? Because for negative, the sign can change, and it's obviously going to be a little bit different. Right. So if we have a positive binary number, I mean, if we shift it 1 place, it's going to half. Okay. If we shift it 2 place, well, it's going to quarter. Right. 3 is going to eighth, and then here it's going to divide by 16. So I mean, let's just say, I don't know, number is divided by 16. I mean, I'm not sure if that's enough for 2 marks. Maybe divided as 1, and then by 16, right? That'll be the other mark. I mean, I think that's fine. And then, I mean, if you want a more general formula, well, you say it's going to be divided by 2 to the power of n, right? Because if here n is 4. If n is 4, then it's going to be 16. Like if we have a binary shift of, I don't know, 10, I think 2 to the power of 10 is going to be 1024. So in that case, you would say, well, if we're shifting 10 places to the right, it's going to divide by 1024. All right, anyway, guys, I mean, that's all the questions. Now, I think that video was a lot longer than I expected, right? Because I did try to explain things. And maybe the next videos I'll actually be kind of maybe less detailed in writing, right? I mean, I'll probably just use bullet points, although again, for the real exam, you should be writing in paragraphs. But hopefully this was useful, and if it is, then I'll, make more videos, and probably try and go over all of the past papers for IG and also A-level as well. All right, so hopefully see you in the next video.